In the previous video we started looking at generators. We're going to take that a step further now. I've just reproduced the diagram there that we were looking at in the last video. Now, an AC generator, as we saw with the previous video, the EMF that's generated alternates between positive and negative. So the A there in AC generator refers to that alternating positive and negative. The C stands for current, but we'll get to that as we continue to move through. One of the things, though, that we need to identify about AC generators, they require a certain number of things in order for them to work. And one of those is something that I alluded to in the previous video. I'll just make this point first, though. So, four things that an AC generator requires. The first is a magnetic field. And in this diagram above, that magnetic field is provided by the north and south poles. The second thing is that it needs a conducting coil, and that conducting coil or conducting loop is represented by the ABCD. And the next thing then is relative motion between those two. And that basically comes back to that idea of Faraday's law, that you need to have the conductor moving through a magnetic field. Now, in this scenario, the diagram that we've got above, we've actually got the coil rotating through the field. In some circumstances, you might actually have the coil stationary and the magnets moving around the coil. So either way, it doesn't really matter, so long as there's relative motion between the magnetic field and the coil. Generally speaking, most generators will have the coil moving through the magnetic field because the coil will be a little bit easier to rotate than having two magnets around the outside of a coil. In that particular diagram that we've got above, though, we have one other aspect that it's important, and that is basically a suitable connection to an external circuit. And that's the first thing that I want to focus on with this video. Now, if we think about that, the diagram above, if those two wires X and Y were, if wires were connected to X and Y, those wires would very quickly become tangled, as that loop continues to rotate. So that's not going to be particularly useful if we're trying to generate electricity and we've got the wires that are connected becoming twisted, and so it's not a particularly useful scenario. And as a result, we need to have a different suitable connection to the outside world or to an external circuit. And the way that that's done is using slip rings. Now, trying to draw these in a diagram can be a little bit tricky, so we'll have a look more closely at this idea in class using a simple AC generator. So basically, this setup now, so if we imagine we've got those two parts X and Y, so I won't bother drawing the rest of the diagram, we're going to have this setup now where we have slip rings. So a slip ring is literally just a ring of metal, and we'll need two of them because we've got two wires, so we need two slip rings to connect those wires to. And basically all it is that so this wire here from X, we're going to connect it permanently to this first slip ring, so we'll call that one S1, we'll call this one S2, and wire Y will be permanently connected, sorry, that should hide behind, will be permanently connected to S2. So it's going to come in here and be attached to that side. So those two, as the wires X and Y rotate around this way, the slip rings S1 and S2 will likewise be rotating around, but they'll be permanently connected to S1 will be permanently connected to X, and S2 will be permanently connected to Y. Now, attached to those, well, not attached, brushing up against those, we have brushes. Now, they're not brushes in the usual sense, they're just pieces of metal that are permanently attached or permanently in contact with the slip rings, but aren't actually attached to them. So let me just notate this first. So we've got our slip rings here, here and here, and then we have our brushes here and here. Now those brushes are then connected to some external circuit, and we'll just do a simple bulb here as our external circuit. Now what it means then is that as the coil rotates, you may recall we said that as AB comes down, the EMF is generated in one direction. That means that the current will then flow out in one particular orientation through the slip ring, out through the brush, that way, and then through the light bulb, and then back in through the other coil going that way. On the other half cycle, the current is now actually going to be going the opposite direction. So it will flow down through X, out through S1, through the brush, down through the light bulb, and back into the circuit. So the current will be alternating here because the EMF being generated by the loop itself will be changing direction each half cycle. Now, as we know, if we have an EMF and we have a closed circuit, we're then going to generate a current. So once it's connected in a circuit, a current will flow. And that current is going to flow according to Lenz's law. And you may recall, according to Lenz's law, the current is going to oppose the change in flux that caused it. Or more generally, it's going to oppose the change that caused it. And in other words, that's going to provide a bit of a resistive force. So as a result, we're going to see some of the energy that's turning the coil simply overcoming that resistive force due to Lenz's law. So some of the input kinetic energy will be used to overcome that resistive force. So the amount of kinetic energy we have going into the system will always be greater than the amount of electrical energy that we get out of the system. Now, if we think about linking back to the previous video, we saw that as the coil rotates, we have an EMF that's generated. So I'll just quickly reproduce that here. EMF that's generated that is a periodic function as the coil continues to rotate. There are some ways that we can actually increase the maximum EMF and other things that we can do in order to change the nature of the EMF that's being generated. So let's have a look at those really quickly now. So firstly, if we were to rotate the coil faster, and we're going to say that by that we're saying we're increasing the angular speed. So that's the technical way of referring to it, or in other words, more simply, how fast the coil is rotated. We're going to change two things. Now, obviously, if we're rotating the coil faster, the first thing that's going to change is the frequency. So increasing the angular speed increases the frequency of the induced EMF. So that means that the instead of having the period as shown there, we might then see that the period will decrease as the frequency increases. So that's the first change. The second change that's important here as well, if you think back to that graph of from the previous video, the rate of change of flux linkage is what determines the maximum EMF. So if the flux linkage is changing in a shorter period of time, it means that the gradient will be steeper, and therefore the maximum EMF is going to increase as well. So there's two things that can change by simply changing the angular speed, or how fast the coil is being rotated. There are some other ways to change the maximum EMF. And if you think about the scenario that we're dealing with, that first point, if we think about the equation that EMF is equal to negative n delta phi on delta t, what we're really doing for this first point here is changing this quantity here of delta t. The other ways that we're going to consider now are looking at what happens with the numerator, the n delta phi. And if you think about that, take that a step further as well. N delta phi is really equal to n multiplied by the change in B times A. So they're the three quantities that we need to consider if we want to change the EMF or increase the EMF in a different way. So the first way that we can increase the EMF is, or by changing the EMF, is by changing the magnetic field strength. So if we increase the magnetic field strength, we're going to increase the flux, and so that will generate a greater EMF. The second way is by changing the area of the loop. Or of the coil itself. And again, if we increase that area, then we're going to increase the EMF. And finally, the last way is by increasing the number of coils. So if we've got more coils, we've simply got a greater flux linkage because there's more area, ultimately, for the magnetic field strength to pass through. So there's three ways that we can change the EMF. I should also mention here, this is going to change the maximum EMF without changing the frequency. So if we change the frequency, we can change the maximum EMF, but we'll also change if we change the angular speed, we'll also change the frequency. So those three methods won't have any effect on the frequency, whereas if we change the angular speed, it will affect both the maximum EMF and the frequency of that EMF as well. We'll have a little bit more of a look at those ideas in class to really sort of make sense of how those things can affect the maximum EMF.